Hi everyone, today we're going to learn about the entropy change of a reaction and the Gibbs free energy change of reaction as standard conditions. Tying to a learning objective from the College Board 5.14, the student is able to determine whether a chemical or physical process is thermodynamically favorable by calculating the change in standard Gibbs free energy. Now, we use this ΔS0rxn to represent standard entropy change. That means the change in entropy for a process in which all the reactants and products are in their standard states. For gas, it's 1 atmospheric pressure. For liquid and solid in their pure form. And for solution, it's 1 molar. And remembering that entropy is a state function, so it's final minus initial, or the entropy change of product minus that of the reactant as standard states. S sub 0 or S super 0, standard molar entropy. The third law of thermodynamics says that the entropy of a pure crystalline substance is 0 at absolute 0 Kelvin. So for the oxygen, we look it up from the textbook, a table in your textbook, 205 joule per Kelvin. For sulfuric acid, 157 joule per Kelvin. And for chromium 3 oxide solid, 81 joule per Kelvin. And we can conclude that the entropy change at standard conditions is greatest for gas, followed by liquid, followed by solid. Entropy increases because there's increased motional energy resulting from increasing temperature. Now look at this diagram here. We can see that as temperature increases on the x-axis, entropy on the y-axis increases from solid to liquid to gas, because now we have greater motional energy for the molecules. Notice that there's a sharp increase, a vertical line when the solid melts into liquid or when the liquid boils into gas, because now they have greater volume for the movement. Molecular speed also increases due to greater kinetic energy at higher temperature. Let's examine the factors that would affect relative standard entropies. 1, the state of matter. Are they gas, liquid, or solid? 2, dissolving. When the crystalline solid dissolves in the water to form ions, we have greater energy dispersal and the entropy increases. 3 will be the molar mass. If we have increasing molar mass, that means there are more places to put energy, and the greater is the dispersal of energy. If you look at helium and neon and argon and krypton and xenon, the series of noble gases, we notice that there's a trend of increasing entropy due to greater molar mass. The fourth factor is allotropes, meaning different forms of the same element. For example, if you compare diamond with graphite, both of which are made of carbon atoms covalently bonded together extensively. Now, in the graphite, we have two-dimensional network covalent. These sheets of graphite, they can slide past each other that are connected by the weak p orbitals. They have greater freedom to move than the interlocking three-dimensional network covalent bonds of diamond, which is very rigid and locked in place. So in different allotrope form, they can have different entropy. In this case, graphite has greater entropy than diamond. And finally, the molecular complexity. The complex molecules, they can have translational, rotational, and vibrational motions. The more complex the molecule, the greater such motions. If you compare NO with NO2 with N2O4, as the molecule becomes more complex and the entropy increases. Now here's a diagram showing the vibration motion that the atoms can vibrate either away from each other or towards each other or toward one side, or the atom or the molecule can spin on its own axis. These are the motions of molecules affecting entropy. calculating standard entropy change of a reaction, which is equal to the summation of the entropy change of the product multiplied by their respective moles minus the summation of the entropy of the reactants multiplied by their respective moles. So find the standard entropy change of a reaction for the combustion of propane. Now, this is equal to product minus reactant. So looking up in your textbook, in your table, you can find this entropy, standard entropy values is 3 moles times that of the carbon dioxide and 4 moles times that of water gas minus 1 mole times propane and 5 moles times the oxygen gas entropy. And this is calculated as 100.3 joule per Kelvin. Remember, entropy change is always recorded as joule per Kelvin per mole. Now we can calculate delta G0 of the reaction. First, we calculate the enthalpy change as standard condition for the reaction in a similar fashion as we did for the entropy change. Again, it is product minus reactant multiplied by their respective moles with the enthalpy values. And this is calculated as negative 2043.8 kilojoule. Now we can then plug the values into the Gibbs free energy equation by putting in the enthalpy, which is negative 2043.8 kilojoule minus the temperature at room temperature 298 Kelvin times 0.1003 kilojoule per Kelvin for the standard entropy change. And the Gibbs free energy is calculated as negative 2073.7 kilojoule. That means the reaction is spontaneous because delta G0 is negative. There's another way to calculate Gibbs free energy change of a reaction from the Gibbs free energy of formation. Now this is equal to the summation of the Gibbs free energy of the products minus that of the reactants multiplied by respective individual moles. So this is a calculation here. 3 moles of CO2 and 4 moles of water minus 1 mole of propane and 5 moles of oxygen. Looking up those values from the table in your textbook, we substitute them in and calculate the delta G0 to be negative 2074.2 kilojoule. Now notice how similar or close in value this one is to the previous calculation. There's another way yet to calculate the delta G0 of the reaction from a stepwise reaction. For example, we want to calculate the Gibbs free energy change as standard condition for the decomposition of calcium carbonate solid into calcium oxide solid and CO2 gas. Given that the first equation is calcium and CO2 and half a mole of O2 to form calcium carbonate. Delta G0 of the reaction negative 734.4 kilojoule. Now then the second equation is 2 moles of calcium solid and 1 mole of oxygen gas to make 2 moles of calcium oxide solid. Delta G0 of the reaction is negative 1206.6 kilojoule. In order to achieve the target equation, we first have to reverse the first equation because we want calcium carbonate to be on the reactant side. So when we reverse the reaction, the sign of the delta G0 is also changed from negative to positive 734.4 kilojoule. Secondly, we need to divide the second equation by 2 because we want to have only 1 mole of calcium oxide. So we take that value of negative 1206.6 kilojoule divided by 2, coming up with 603.3 kilojoule. Now you add up the 2 equations, you will obtain the target equation, and you will also add up the delta G0, which is equal to 131.1 kilojoule. So I just gone through the 3 ways to calculate the Gibbs free energy change at standard conditions for a reaction. We learned today that the entropy is dependent on temperature. The higher the temperature, the greater the entropy. We also learned that the relative standard entropies will depend on the states of matter dissolving a solid in water, the increasing molar mass, the different forms of allotropes, and the greater molecular complexity. All these will increase the relative standard entropies. We also learned how to calculate the entropy change of a reaction at standard condition by taking product value minus reactant values. Finally, we learned how to calculate the Gibbs free energy change of a reaction from 3 ways. One is from the entropy and the enthalpy change of the reaction. Secondly, from the Gibbs free energy of formation. And finally, by adding up the steps and manipulating the equations to add it up to the delta G0 of a reaction. I hope that you have found this video helpful to your learning. If you like it, please give us a like. And I look forward to seeing you in the next part of thermodynamics.